Hello and welcome to another OpenGL, SDL and C++ tutorial. In this tutorial I want to go over the 3D collision detection, and actually I just want to do two kind of 3D collision detection: the sphere-sphere collision detection and response, and the sphere-plane collision detection and response. Why I choose these two geometric objects to do the collision detection? That's fairly simple because it's easy to calculate with them. The sphere is very simple, just the center point and the radius, and the plane is not so simple, not as simple, but it is necessary for the walls and everything else basically. So we made up from planes the entire map. So I say let's get started. I think this is a bit simpler than the ray tracing was, but we will use the ray tracing here too, so basically we use that too, just we don't have to calculate it again. Okay, so sphere-sphere collision detection, that's kind of simple. We just have two sphere, as you can see in here, although these are just circles, but represent a sphere. And if the radius, so the distance between the 2 points, is less than the sum of the two radius, so the R1 plus R2, then there is a collision detection. I think it's kind of obvious, mostly if you draw it like me. And so let's go to the next frame. First of all, we need to get a vector which points from the center point 1 to the center point 2. And you get a vector from 2 points by subtract the start point from the end point. As you can see, you subtract vectors by subtract the corresponding components. So you get the C2.x minus C1.x, and the same with the y and the z coordinates. Now you have a vector which points from from C1 to C2. Now you need to calculate the length of this vector, which is again kind of simple. You use the Pythagoras formula to do that. We already did that, so I don't think that's kind of new to you, but if so, this is how you get the length of any kind of vector. You can easily represent this with a right triangle. Okay, so next frame. Now how do we react? Because we don't want only to detect collision if there is a collision or isn't there a collision. We actually want to move one of the sphere so it cannot go inside the other sphere. Okay, so basically all we do is get how much this blue line, I don't know, do you see it? So this blue line, how long is this? And then in the direction of this vector you just move this second sphere. So first it go inside, but we don't render that. Now we calculate if there is a collision. If so, we calculate how much inside, so how much the second sphere is inside the first, and then we move exactly that much in the direction, in the different direction. So, for example, this line is 1 long. Then I get this vector, which is a vector point from C1 to C2. You already seen that. We normalize that because if we want to represent a direction, we want a normalized vector. This is kind of good habit, but actually in here you actually need that. And then lastly you multiply this vector which points from C1 to C2 with how much we are inside. So for example, in case of 1, if you multiply this one vector with 1, it will not change. So basically you will move 1 unit in this direction where this vector is 0.2. So basically you move out this sphere from the other sphere. That's the trick here. If you like to read, then read this, but basically I said the same, I believe, just I don't have a right place to do it. Okay, so now that was the sphere-sphere collision detection, and I would say before we go on to the sphere-plane collision detection, let's actually implement that. And okay, here is the program which we have written in the last tutorial. This is kind of simple. I've already forgot what this does, but we can easily find out by run the program. Okay, as you can see, we already have a sphere right here, although we can go through it, and we have a plane. This is the perfect place to test our two collision methods which we will write. So I will try to go inside this sphere after we implement the collision detection, and if I cannot, then it means that it is working. Okay, by the way, probably you have already noticed that I don't want to put another sphere here and move that sphere inside that. I actually want to put an imaginary sphere around the camera and try to go with the camera in this object. So it will be like a real collision detection. We don't want to do it with sphere, because who cares what sphere does. Alright then, now we can start to making the program. Okay, before I go on to the actual collision detection, I need to add two more variables, two more parameters to this 3 sphere and implement a little bit more, because we need to get the direction, the distance of where does the collision happen. So now I add a float parameter here, actually a float pointer parameter here, because we want to be able to modify this, and I call it distance, distance. Okay, and I set it to null. This is a default parameter, so you don't have to give this parameter, and yeah, it will be null if you don't give it. If you give a pointer to this, then it will not null. That's what we care about, and we need to actually get the position where does the collision happen. So I make a coordinate. This coordinate structure is inside this object loader header file, so if you are interested, basically it just store free point x, y, z coordinates, so that's why it is called coordinate. Okay, and I call it, I don't know, point, because why not? Okay, and actually I add the same two parameter, not just here, but to the ray plane collision detection too. Oh, and we need a null to the coordinate. Null is basically means that it do not point anywhere. Null. That's right. Now let me implement this. So if it is not null, then we give the point and the distance to it. If it is null, we don't have anything to do with it. So let's try to find ray sphere. Perfect. Okay, so we have a float pointer, and this was a dist, and we have a coordinate pointer. This was the point. Okay, by the way, you don't put the default parameter here like that, because it will give error. You put the default parameter in the header file and you do not put in here, or you put in here but you don't do it in the header file. But don't do it in both places, because there will be a problem. Alright then, now else, if it didn't return with false, then we have a collision. Now we check if the distance, so this distance pointer is null. So if dist equal to null, not equal to null, because if it is equal to null, we have nothing to do with it. So okay, so if it is not null, then it will execute this if statement. If it is not, we just return with true, indicate that there is a collision. We will return true anyway, but we will return with the distance. Okay, now set the distance. Set the distance equal to let's calculate the distance. So the solver of the quadratic equation looks like something like this: minus b plus and minus. So first collision point will be plus and the second collision point will be minus. So plus minus b square minus 4 times a times c, and this whole thing is divided by 2a. Okay, we already clarified that a is 1, so if I multiply this 2 by 1, then it will be 2 anyway, and if I multiply the 4c by 1, it will be 4 anyway, so I delete those. And as you can see, this is here, this is the discriminant. We already wrote that, so we can write the discriminant here, and that is what we have to calculate: minus b plus the discriminant divided by 2. That will be the distance of the first collision point, and for the second collision point it will be minus. But I think one collision point should be enough for us. If not, we just put an array in here and then rewrite this to calculate both of the collision points. Okay, so minus b plus discriminant, and this whole thing is divided by 2. that's it. So we calculated the distance. We use the indirection operator obviously because we don't want to set the address, we want to set what it is point to obviously. Okay, and now if the point is not null, so if point not equal to null, okay, then we calculate the point, which is kind of simple. So point x, we use this arrow operator, which is obviously a structure pointer, so we get the x member variable and we set it to, don't forget, we have to rewrite this this distance, which is the t. Actually I could call it t if I want, but I call it distance. So we rewrite this distance to the original ray formula, which is looked like start point, so xs plus t times xd, where xd is the direction, so the x component of the direction, t is the distance which we have calculated, and xs is the start point. So xs, because I call it xs in here, this is the start point of the ray, plus the distance. Don't forget we have to use the indirection operator like that, because we want to actually calculate with the value, not with the address, and times the direction, so the x component of the direction. I do the same with the y and the z too. So here y and ys, and in here yd. Again it's z, zs and zd. Now we set the point where the collision happened. So obviously we only check if the point is null if we get the distance, as I think it is needless to check. Alright then, so if this 2 is null, we don't have to use the resources to calculate these, and we can actually just return with false or true. But if it is not null, so we actually want to know where does the collision happen, then we can just pass the address in here and we get it. Okay, originally I didn't wrote this because originally I thought I make another function called ray sphere distance and ray sphere point, which will return the distance and the point, but that will be a whole waste of resources, so I rather recommend that. That's why we rewrite this. Okay, and actually I will go through this second thing a little bit quicker. So this is the ray plane, so a float pointer distance and a coordinate pointer point. Okay, and again before I return with true, so here I make a parenthesis where the collision happened, and I check first if the distance is not equal to null. If it is not equal to null, then we pass some pointers, so make the distance equals to the t, because we already calculated the t right here. As you can see, we already calculated the t, and we already calculated the points as well. So again, if the coordinate, point, if the point is not null, then I just set the point x to x, the point y to y, and the point z to z. Alright, that was it. So I made a little change. Now let's see if it is compiled or not. Okay, I think it should be compiling. Oh no. Yeah, there is a problem in 236. Oh, I write disk, so discriminant instead of distance. Yeah, that's the best thing if you call the names so close to each other, because this is so close. By the way, the error message was that invalid type argument of, yeah, that's the error. Okay, that because we want to get the what point to, so we want to get what the discriminant point to, but this discriminant doesn't point anything because it is actually yeah, it is a variable, not a pointer. Okay, so yeah, the program is running. So I don't know, I didn't check that the values are correct, but I guess they are. So if not, later on we will get back here. Alright, then let's write the toCollision function. It will return both bool, which will represent is there a collision or not, obviously, and I call the first sphere collision detection, and we need a coordinate C1. Again, the coordinate is inside the object loader header file. It just contains 3 floats, and we have a float R1, so this is the center point for the first sphere, and this is the radius of the first sphere. Then make the coordinate C2 and float R2. Pretty simple. So let me just copy this to save a little bit of time, and I will implement down here under everything else. This will be a pretty useful function. Later on it will be a pretty useful member function. So yep. Okay, that's right. Now, okay, so let's start to implement it. First of all, we need to get the distance of the center point, and for that actually I will make another function, because we calculate the length of 2 points quite a lot. So this will return float and point distance. By the way, I made a vector class, not a vector class like std vector, a vector class like 3D vector, and I implement a lot of useful member function. What am I doing? So coordinate C1, coordinate C2. So I implement a vector class which is pretty useful and saves us from a lot of typing. Like, we don't need to make this this point distance. If I use that vector class, I can just use the length member function and it will return with the length, so I don't have to write a separate function for that, but I will implement that vector later on. Okay, so this will be float point distance, okay, with 2 coordinates C1 and C2. Okay, and we will return with the distance of the 2 points. So again, I use the formula that first of all we get a vector from the 2 points. So a vector which points from C1 to C2. Let me create that. So it will be a coordinate like vector, and I subtract the start point from the end point. So C2.x minus C1.x, and I do the same with the y and the z too. I subtract the endpoint coordinates from the start point coordinates. So this is the y, and this is the y, this is the z, and this is the z. Okay, that's how you create vector from 2 points, which is actually pretty useful. If you not know this already, you should learn this, because you will use it a lot. For example, with this method we will calculate where the zombie will go in the zombie game. Oh, by the way, a little bit of announcement of the zombie game, a zombie FPS game which I am making for this tutorial, for this channel. I am almost finished. Most of the programming is ready. Now I have to make the models and animate them, reload animation, and a lot of crap. So probably 1 or at max 2 weeks. Don't be afraid about that. It takes me so much time to make it. That's just because lately I do not have too much time about making it. Okay, but let's continue with the tutorial, because that's what we are making. So we will return with vector.x times vector.x plus vector.y times vector.y and plus vector.z times vector.z. Okay, and actually we need to get the square root of this. So sqrt, and yeah, get the square root. And actually you know what? We don't use the square root right now. I will show you a trick which will increase the performance a little bit. Okay, so we return with the distance square, so the point distance in squared. Okay, so now we can get this distance. So I make a float, again I call it distance, and I use this point distance which is here, and I put the C1 and the C2 in it. One more thing which I wanted to say is you may want to use references in here. Actually in float you can use references, it will increase a little bit, but in coordinate this is actually free float, not one float, so it is you should use it, but only if you don't want to create a vector while you call it. So if, for example, if you call it like this, sphere, this is in the main function or somewhere, just call the function, and then if you pass the parameter like that, so coordinate, and you just find out a number, that will not work because this is a temporary variable. So now if you pass that in, then it will give a compile error that cannot get the address of reference, cannot get the address or reference of the temporary variable. So only if you store once before it, so if you coordinate C and then here store the coordinate, then you can pass the C as a reference. So yeah, that was a little announcement. I don't know, do you know it or not? Probably you know, but you know, just make sure that you know. Okay, so I just removed the references because we will, for this test purpose, we will just create the coordinate like that as you saw earlier. Okay, so we get the distance. Now it is time to find out is there a collision or not. So if this distance is less or equal than the R1 plus R2 times R1 plus R2, so this means so that's I squared the R1 plus R2 in this way. Instead of get the square root of this distance, I actually put the square, the R1 plus R2. Why is this good? Because the computer can easily calculate a multiplication than a square root. It is true for me. I can more simpler can calculate a multiplication in paper than a square root in paper. So that's why it is a little bit increase the performance, probably not much, if any. So now we need to get the vector, which is yeah, this small vector, right? So this small length or right here. So that's the blue one. Okay, let me. So we want to get this. How long is this? So you can get it by get the distance between the two. So between the C1 and the C2. Distance between the center point 1 and the center point 2 is, for example, 9, because why not? And the R1, so the radius 1 plus radius 2 is 10. Then we know that this little bit of thing is 1 length long. Now if I if I subtract this little, so then if I subtract the R1 plus R2 from the distance between the 2 points, I get a number. For example, in the earlier example, if the length between the two is 9 and the R1 plus R2 is exactly 10, then I get a -1. So this means that we multiply this vector by -1. So this vector which points from C1 to C2, and it is normalized obviously. And if I multiply it by -1, it means that we have to move this second sphere -1 times this vector. So we will move something like this will be. So we move a little bit back before we render, obviously. So we will not render anything, we will not draw anything in the scene while it is inside this other sphere. We only draw after it gets out from the other sphere. So we cannot even see that it was inside the other sphere. So let's do that. It will make sense if it is not. So make a float variable, call it a, because you know why not. And I get the distance. Now I use the square root distance. I will only use the square root if there is a collision. Most of the time obviously there will be no collision, so I will not use the square root. That's why it is still better. Okay, and then I subtract the R1 plus R2 from it. R2. Okay, so basically we will get in the earlier example -1 here, or -2 or -10. So that means that we move 1, 2, 10 units in the distance of the vector which we will now create. Okay, the vector which points from the C1 to C2 is, as you have already seen in this tutorial, the start point from the end point. So I create a new coordinate, I call it vec because why not, and c2.x minus c1.x, c2.y minus c1.y, and c2.z minus c1.z. By the way, the vector class which I have written has an overloaded minus, so subtract operator, and it is just as simple as write c2 minus c1, so I don't have to write this lot of crap, just this two thing. But yeah, that was it. I think I haven't typed it, but it could happen because yeah, I always type, I have always typos in it, but the compiler will tell us. Now we need to normalize this vector. To do that, we need to get the length of this vector. By the way, there is a length variable and a member function and the normalized member function in that vector class, so I don't have to write this neither. Okay, so float, I call it len, like length, and obviously I use the Pythagoras theorem again, so vector.x times vector.x, vector.y times vector.y, and vector.z times vector.z. Okay, did I type it? Yes, I did. Alright, is it good now? I think so. Okay, so we get the length, and to normalize a vector, we subtract each component with the length. So vec.x divided equal to length, and vector.y is divided equal by the length, and vector.z is divided equal by the length. Okay, that's it. Now we have a normalized vector which points from C1 to C2. Now we only need to calculate how much do we want to move the sphere. Oh, one more thing, I almost forget it. We need to create, so this first parameter has to be reference, not because it has more performance, although it has, but because we want to change this C1 value. And we can change the C1 value if it is a reference or a pointer. If it is just copied, it will be like this. We cannot change it. There is a local variable C1, we can change it, but there will be no effect of the parameter which have been passed to the function. So we need to pass by reference. Alright then, so now we need to calculate the new coordinate, so c1.x, and make the c1.x the c1.x, so the center point, plus this vector.x times this a which we have calculated. So for example, if the center point was 0, 0, 0, like that, this was the center point, and the vector is point to, don't know, 1, 1, 0, 0, and we have minus 1 as the parameter. This will mean that the new position of the sphere will be minus 1, 0, 0. That will be the new position which we will return. Not return, but actually change it to that. Okay, and then we have to do again with the y and the z. I have the overloaded multiplication operator too, so I don't have to use the time. It is actually just one line. And yeah, that was it. And I think I haven't typed it. So if I haven't typed it, it should work. Now I return with true right here, so I return with true, and outside of this if I return with false, because we get this if only if we have a collision. So if we have a collision, we return with 1, calculate the new position of the C1 sphere, and return with false. Okay, I think it's time to try it out. So I go here in the fur.cpp file. This is the same as it was. Yeah, one more thing I forget. We actually have to move the camera. We cannot use this move camera thing, so we actually need to be able to change these this cam x, cam y, and cam z coordinate. So actually I will make a function for that, although I could just write this float variable right here in the header file, and then it will be global, so I could use them, but rather I will write a function for that. So void and move to, and it will wait a coordinate. Okay, I call it C because why not, and I return with the coordinate right here, and I call it cam pos, like camera position, and this will wait no parameter. This will be just one line, so we can quickly implement it with no problem. Okay, so I set the cam x equal to c.x, the cam y equal to c.y, and cam z equal to c.z. Okay, that's it. I think that was cam x, y, z. Yep, it was. Alrighty then, let's make this cam pos, which will return with a coordinate which will contain the cam x, cam y, and cam z. That's right. Okay, now we can actually try to use this. So I go to the main function right here in the main, right there. Okay, and after this lot of thing I will implement it. So first we need to find out what is the coordinate of the sphere. You know what? No, I make an if statement, sphere. Okay, first we will need our coordinate, which will be returned by this getPos campos function. So I make a coordinate function, I make it campos camera position, and make it equal to campos. Alright then, and I pass this camera position to the first parameter, camera position. What the radius should be. I tested a little bit, and 2.0 seems okay. If it is bigger, if it is greater, then I can go closer to some value. If it is smaller, then I can go through. So we will need to find a good value. 2 is approximately okay, but we can change it with backspace and the number on the keypad. Okay, and now we need to find out what is the coordinate of this other sphere which we have seen. So the coordinate of that sphere, yeah, I will find in a moment, don't worry. It pretty much seems that it is 0, 0, 0 coordinate, because I cannot see any translation before this call. So I think it is 0, 0, 0 coordinate, so I will pass that. So coordinate 0, 0, 0. And the last parameter is the radius of that sphere. I believe this is 1.0. Okay, and if this happens, just write something out. So cout actually, console output collision, and I make a new line here. But this will not actually matter, because if this sphere is actually called, this will change this camera pose to our new position, so we need to move the camera to the new camera position. So what was that? Call is move to and camera position. So basically all we did is calculate if there is a collision. If so, we calculate a new position for the first sphere, and then I move to this new position. Alright, now we need to find out how much error did I make. So g++ star.cpp -lsdl -lgl -lglu. Okay. Oh, just one error. This is impossible. I don't make usually less error. I usually make much more errors. We will find out in a moment. Yep, undefined reference to sphere. Oh, I know what the problem is. I changed this first to a reference, right here, a reference, but I didn't change it in, so I changed it to a reference right here, but I didn't change it in the header file. So it is actually seems as an overloaded function. So this means the same. If I delete this, this is the same. If this is a different function than this. So that's what was the problem. Okay, now, yep, it seems to compile. Never mind, there will be other kind of errors, I believe. So try to go inside. Yep. Hop. Yep, the collision is actually working good, so I make the errors elsewhere. I will find out in a moment where exactly the error happened. Yep, I find it. Copy and paste error. So I should make a new error type called copy and paste error, because I always make copy and paste errors. Okay, now it should work. Try to compile it again. So by the way, you have seen the error. This O was X instead of XYZ. Yep, let's try to make it run. Now, if still not perfect. Nope. Okay, I made a very stupid mistake. Actually, two of them. When I calculated the length, you don't calculate the length as multiply them and put commas in there. What the hell is that? So probably I wasn't really make attention then. So we need to add the square of these values, so x squared plus y squared plus z squared, and we need to get the square root of them. That's right, that was the last error. I tried it out and it's worked now. So I can compile now and I can run it now. Okay then, so now if I wanted to go inside the sphere, I cannot, as you can see. Not matter how hard I press the key, it not goes inside. I can go through, I can go here up, but I cannot go inside them. No way that I can go inside that. Alright, and this part of this tutorial is work, so yep, yippee. If I wouldn't make this stupid error, it would be quite nice. The number of errors was quite less, so it will be quite nice. Alright then, let's go back